In this video, we're going to learn how to convert calculus into algebra so that we can solve a system of linear partial differential equations, like the linearized heat equation here, the linearized heat equation, the evolution of T1 for time derivatives and spatial derivatives. How do we take a linearized partial differential equation like this, convert the calculus into algebra, and then solve the system? The tool that we're going to use for linear systems is what's called polynomial approximation theory. So polynomial approximations. A polynomial approximation is a way of representing a function. We're going to let there be a polynomial representation of a function, like our function of temperature. We're going to call it P sub n. We'll think just spatially to begin here. We're going to say that there's some polynomial that approximates some function that we want to understand. So P sub n, this is our polynomial, and it's got a degree of n in this representation. So if we have a polynomial, P sub n, that approximates a function, what do we actually mean? So what a P sub n is a sum, a collection of a whole bunch of individual polynomials. It's a linear combination, and a sum, a linear combination of individual polynomials. I'm going to represent them as a phi here, sub j, which vary in space. And each polynomial, it's a linear combination, each one has a weighting, a c, a coefficient. And a polynomial representation is a sum over all of the basis functions weighted by their coefficient weights, coefficients. These basis functions might be something like sine and cosine. They might be something like a complex exponential, e to the I k x, or they might be something more interesting like a Chebyshev polynomial or something else. But these different polynomial basis functions summed together in a linear sum can represent arbitrary functions f. Now, if we have a polynomial approximation to our function f, then there's an interesting property I'm going to show you. So then, if we have a polynomial representation of our function, then an interesting thing is that if the polynomial approximates f, then the derivative of the polynomial itself approximates the derivative of f. So the unknown derivative of f can be approximated to the same degree of accuracy by the derivative of the polynomial that approximates it. Why is this handy? Well, we know derivatives of polynomials. We don't know derivatives of arbitrary functions f. But if we can figure out how to represent the function f as a collection of polynomials, then we can also represent its derivative as a collection of related polynomials. Now, what polynomials do you use? Well, to make further progress, we need to know something about our problem. What polynomials do we use? What basis functions do we use? To answer this, we have to know something about the properties of our problem. If we're lucky, and if we have a simple system, then we may be able to use some simple polynomials. And what we need to know is we need to know about the boundary conditions of our system or other properties. Now, in certain systems, we can use a very convenient set of basis functions, which are the exponential basis functions. And there's a very handy fact about exponentials. Handy fact. So the polynomial representation of the derivative, it's possible that the derivative changes the polynomials, but there is one class of polynomials where the derivative does not change them, and these are the exponentials. So the exponentials, e to the kx, e to the kx, so let phi sub j of x equal e to the kx, where k is indexed by j. It's some wave number k, e to the kx. If we have basis functions that are the phi sub j's that are built out of exponentials, these basis functions are the eigenfunctions of the derivative operator. So if we take d by dx of the exponential function e to the kx, then the answer to that is itself k e to the kx, or it's equal to k times our original basis function. The basis function hasn't changed, it's just gained a new weighting by the wave number k. So exponential functions, when we take a calculus operation on them, a derivative operation on them, they're the eigenfunctions of that operator, and the eigenvalue of that operator is the wave number k. Here's our eigenvalue, and here's our eigenfunction. Eigenfunction and eigenvalues. All right. Now, when can we use these? Well, if we have, if our boundary conditions are periodic, or, and sort of equivalently theoretically, or if our system is infinite and homogeneous, then we can represent our solution, our function of x, by a particular set of exponential functions, which are the Fourier series. So we can have a sum of the c sub j's of our phi sub j's of x, j, where our phi sub j's, c sub j, are e, and they're complex exponentials, I, k sub j of x. And this will be a very good, and in fact exact in the infinite limit, representation of our system. A similar argument applies in time. If we don't have, if time is infinite, and if time is everywhere the same as homogeneous, then in the same way, also, we can have basis functions in time, maybe call this a capital phi for the moment, sub j of time, that are e to the I omega t. We'll often use a minus sign as a convention here, especially as we go to our partial derivatives. All right. So a powerful concept is that if we have a system where we can represent our system, a powerful concept is that if we have a system where we can represent, our function in terms of Fourier polynomials in space and time, then if we consider the Fourier transform of f, so I'm going to call this f hat, this is the Fourier transform, f Fourier transform of f, with f being given by the sum of the weighted coefficients with e to the I kx minus I omega t. If we have this system, then when we take derivatives of this, then d by dt of f hat is equal to just minus I omega f hat. And d by dx of f hat is I k f hat, because the Fourier system here is the eigenfunction of both the time and space derivative operators. All right, let's come back to our heat equation that was at the top of our lecture. So let's consider our heat equation again. So consider our heat equation, d by dt of T1 minus chi del squared T1 equals 0. So if I go to the Fourier space, go to T hat, if I consider the Fourier space, which is the Fourier, the coefficient space, as we sometimes call it, the Fourier transform, I can solve my calculus problem easily in the Fourier space by taking the Fourier transform of my problem and then using the fact that the Fourier polynomials are the eigenfunctions of calculus to replace my derivative operators and rewrite my heat function within the Fourier space. So I'm going to do that right now. So I'm going to come through and I'm going to bring down one temporal derivative. This is our d by dt. And we have two spatial derivatives. This is my Laplacian, my d by dx squared. And this also operates on T1 hat. Now this must be 0 for any T1 hat, which tells us something very profound. This tells us the relationship between the omega, the temporal variation of this mode, and the k, the spatial variation of this mode. So this system has the solution that omega is equal to minus I times our diffusion coefficient chi times k squared. This is the required condition to have solutions to the heat equation. Is that surprising to us? Well, let's take a look for a moment at what this implies for T1 itself. So if we consider our T1, our coefficient space fluctuation, this particular Fourier component, this has some c sub k, some coefficient for its given k. It's got an e to the I kx, that's its spatial eigenfunction, minus I omega t. And if we now take this solution for omega and plug it in, we can see that the temporal part of this has the form of e to the minus I squared. So it has I squared, but I squared, that's equal to minus 1. And so this has the form of e to the minus chi k squared t. This is related to the thermal diffusion time. Remind you that the thermal diffusion time, tau, thermal diffusion, this is equal to 1 over our thermal diffusion coefficient times our wave number squared. And so this whole form here is the form e to the minus T over tau, so chi, and we find our known solution to the heat equation, which is that under diffusion, all perturbations exponentially decay away with time, and the rate at which they decay is related to their wave number, to their spatial scale. In our next lecture, we'll learn how to use this tool to solve a system of equations to solve for waves in a simple atmosphere.